So this is a short introduction to Geospatial JS operations in Julia. On this tutorial, we are going to focus a lot on geography. How can you import polygons on Julia, create operations with those, for example, offsets, or create your own polygons on Julia and then export those to your JS application. So why working with maps? There is a lot of data that can be located on the world itself, or it can be extracted from the world. This type of data has a geological spatial context and either needs to be extracted from a world model, or it will benefit on being displayed on the map. For example, you might want to plot the locations of a service on the map and show to a client what is the closest one to his current location. Maybe you want to plot the effects of a flood in order to identify what towns are going to be in risk and are going to require some help in such scenario. For those tasks, you are going to need to work on top of the Earth's geography, either to extract the data or to output your results. Sadly, the Earth itself, it's not geometrical. The word geography is so complex that we might only approximate with actually a geometrical shape. The closest one will be an ellipsoid that you can see here on the right. Let's imagine that the Earth itself is going to be our topography, this brown line over here with a lot of elevations. You either got valleys, mountains, or the depths of the sea itself, and we can only approximate it with a model. The closest one is this ellipsoid over here, but of course there is always going to be an error. But anyhow, having this blue model over here allows us to use two angles, a latitude and longitude. And with only those two angles, we can pinpoint a location on our model that, on this case, it's the ellipsoid. And of course, this model has a lot of math and a lot of approximations in order to allow us to have the lowest amount of error as possible. The most common ellipsoid, so this model that covers the old world, is WGS84. This is very famous just because it's a datum that is being currently used on GPS and has been used for a long time now. We can't easily measure distances with these angles, so it's good for us to pinpoint a location itself. But if we want actually to do operations like offsets, so adding some distances or subtract some distances, then for that, we actually don't want angles, we want a distance in meters. So to easily do measurements, we need then a flat surface. Of course, the Earth itself, it's not flat, but we can create a projection of a small area of the Earth itself where the error is enough for us, is acceptable. So any type of distortions that are applied with this projection will create an error that for our application, it's okay. By assuming then a projection, we can now working on a planar Cartesian coordinate system. So X and Y, your normal 2D plot. This will always have an amount of distortion, of course, because we are forcing a flat projection of something that it's, well, approximately round and can be modeled with an ellipsoid shape. The most common one is UTM, Universal Transverse Mercator, that divides the globe then on these small patches where we can accept the distortion is not too much. So on this tutorial, we'll create and read KML files with polygons, but also points. The first package is going to be GMT, Generic Mapping Tools. It's a mature package. It has tons of options. It's called a Swiss knife in terms of mapping tools. It's very extensive. And what we are going to use is going to be a Julia wrapper. So a way to map the original functions with something that can be called from Julia. And we're going to use this to interact with the toolbox. So we will import these KML files that are described within WGS84, and then we are going to convert those to UTM by using another package from the JuliaGeo package, more specifically Geodesy.jl. Then we are also going to import Julia-generated KML files with Google Earth. That is going to be our tool here for visualization. But for visualization, we can also use the generic mapping tools. It has a lot of functions that allow us to create some maps already directly then on Julia. So interfacing with Google Earth it's not the only option to generate visualizations. Okay, so let's now start the code itself. I'm going to import then the two toolboxes, the GMT and Geodesy. Now let us create a point. And this point that I'm creating, it's going to have a latitude and longitude. And I'm going to call it first x. It's going to be our variable. Then we got our function from the GMT toolbox called GMT dataset that allow us to create an object with these coordinates. First, the longitude, and then the latitude. Okay, and maybe I can already start executing this command. So the package, and now the object. The object, you can see that there is two columns. And now I can start preparing for GMT to output these coordinates to a KML file. For that, I just use the function GMT2KML. And I'm going to call then for our function the variable x. And I'm going to get only the text. Okay, so let's give it a look to see how it looks. Okay, so what I got here is all the text from the KML file. We can give it a look a little bit more in detail if I write it to a file. So I'm just going to do that. And my file is going to be called, well, our output. The extension is very important in order for it to be opened by Google Earth. That is our tool that I want to use here. I use it all the time. It's pretty useful. So output KML. And then you can see here that the output is actually a vector of strings. So it's not an individual string that I can write on my file. So what I need to do is join all of these strings on the data out. And there is a parameter that I can give to the join function that is going to be what I need to write between each string. In this case, I just write /n. That is a new line. So what's going to happen is I'm going to join all of these strings together, and between strings of this vector, I'm just going to create a new line. So it's going to be an individual string. I can show to you guys. It's going to be an individual string, but we then got our /n saying to the file, or actually saying to the application, that what we got here is a new line. Perfect. And now I do have already my KML file. Let's execute it. So a new file was created called output KML. You can see here that now the text tag editor knows that it got a new line after all of these tags. By the way, a KML file is just an XML file with some defined parameters. That is a standard for KML, and it's actually just complying with that standard. So what I can do is just open this. It's actually where we wanted it, but we can confirm by just checking the properties. So here it is, latitude 48.85 and then longitude 2.35. Okay, so now outputting our points from Julia to Google Earth works already. What I'm going to do now is going to be the opposite. I'm going to create a file here on Google Earth and import it on Julia, just to check if I actually can do both ways. So what I'm going to do here is I'm going to define a row. Let me select one that looks horizontal. I mean, we can do it right here. Okay, so what I'm going to do is I'm going to try to delimitate this road over here with an offset. And then I want to compensate that offset on Julia. So I'm going to then, what I'm going to do is just create an offset here of 100 meters. And I'm going to create a polygon, a new polygon here, right on the middle of it. And then hopefully what I'm going to do on Julia, and let's see if it works out just fine, is I'm going to create this offset And this area over here should be overlaid on top of this street. So the polygon is created. I'm going to save it. And I'm going just to call it road. Of course, extension KML. And let's see if I can import the file itself and then creating this offset. The offset, I'm going to work on Cartesian coordinates. So here on the right, X, and then on the top, Y. What I want to do is just add to the Y coordinate 100 meters. That's the offset that I've created here. So here on Visual Studio Code, import poly from Google Earth and move it 100 meters to the north. Okay, let's start our code. First, I'm going to give it the path. Right now, it's located on my C tutorial and then road KML. Okay, perfect. If everything is correct, then it should appear here that we got a new link. Okay, perfect. You see? And you can just control click it and the file opens. Perfect. Okay, so next I want to read this file. And for that, we got the function from the GMT package called GMT_read. Okay, let me run it, see if everything is okay for now. It is, and you can see already, there is the bounding box, but you can see already that we got 5 points. So we imported our polygon and it has 5 points. Now, the interesting part is that I only used 4 points for my polygon. You can see it here. But what happens is a point in the beginning is created also on the end, showing that this polygon is a closed one. And it's not to be handled as a line, but actually a polygon because it's closed. So, yeah, the read work. Now I'm going to try to pick up these coordinates and use a new toolbox because I'm going to need now Geodesy. Everything that I used till now was from the GMT toolbox. I'm now going to use the Geodesy with a function called LLA. So I'm going to create a point with the latitude and the longitude. The altitude I'm not going to use here, but just for you guys to know that you can also use the altitude. I'm going to use the poly. You can see that, maybe I should put it here. Poly has a lot of variables. The one that I'm going to use is data. And the poly data is just a matrix with all the latitudes and longitudes of the polygon that I've imported. So let's pick up all of those. By the way, here is reversed. So that's why I'm using the two first. And now I'm going to use the poly data one. So the latitude and longitude are reversed between those two toolboxes, just for you guys to know. And as I've told you before, I need to create an offset. And in order for us to do this type of Cartesian transformations, I need to have a projection, a planar projection. And the one that I'm going to use is UTM. So for that, I'm going to create our variable UTM z. That is going to call the function from Geodesy UTM z. And in order for the function to know the original reference, I'm going to say that it's going to be WGS84 for all the case on our matrix. Does it work? It's not defined because I still didn't run the function on top. Okay, perfect. You see that this is interesting, and I should explain to you guys that now all my latitude and longitudes are now X and Y. That is also here the altitude and the zone, the UTM zone. Is there any way for me to show you the zone here? Probably. Let me check. So I can just show latitude and longitude on universal transverse marketer. And this is actually the UTM that we are using. And you can see here on the bottom that the area is 31. That, yeah, it's the same as we got from our Geodesy toolbox. Okay, so that's correct. Everything is correct till now. Let us continue. So I'm going to create now a new variable, transformed. And I'm going to create, once again, the UTM-Z object, but now it's going to be a little bit different. I'm not going to convert. I'm just going to give already the values. So I'm not going to convert from WG84. I have all the values that I want. It's just that I'm going to create an offset for the epsilon. So the first values are going to be from the x-axis. And now for the epsilon axis. And this is going to be the one that I'm going to give an offset. Hopefully it's going to be 100, maybe slightly off by some meters. But if it doesn't actually fit the rule itself, I can just change it here. And now the zone. Now another thing, it's if it is north or south. TM, once again for K is north. And now I'm going to run this for all the Ks. I'm just missing here a parenthesis on the end. Okay, looks good. Let me cycle the K. Okay. So hopefully it worked. What we are going to do now is I already did my transformation here on UTM by running this line. Now I'm going to create a transformer that is going to transform my UTM coordinates to latitude and longitude. So it's from UTM-Z, perfect. And the conversion, it's to WG-S84. So I actually can run it first. Okay, it's created. Now I can just use it to convert my coordinates. Don't forget the broadcast function because I got more than one coordinate here. And I need to do it for every single one of those. Okay, you can see that we already got latitude and longitude. The only question now is see if it actually is on the right place or not. I'm going to reuse my polygon that I've previously imported. So I'm just going to get all of my data from the latitude and longitude that was transformed from only my parameters lon and lat, that is the longitude and latitude. Did it work? Yeah, get field is not defined. Ah, because get field doesn't have an underscore. Okay, perfect. And now, well, let's output it and see if it works. If it is on the correct place or not. So same thing as before, GMT to KML. This time it's a polygon, it's not a point. And yeah, this is interesting. As we are now using a polygon and I want to output a polygon, I need to give a new parameter for my function here for the GMT to KML. That is f of the type polygon. You just need to do this. Okay, it seems like it worked. Let us write, well, I can just write on the same file. No need for it to be different. Let's open it and see how it looks. Yes, I want to reload. Oh, and there it is. You can see, guys, that currently it's now on the north. The thing is, the road should be a little bit wider. Should look like this, actually. Well, I didn't need to to create a perfect polygon, but let's just try it to see if we can actually do it. It looks better that way. I'm just going to run all the code again. Open it again. Okay. And it does look better. So yeah, we did it. So what we have done here is we created a polygon and then we exported the KML file with that polygon on Julia. We created this offset of 100 meters. And then we exported once again to KML in order for our polygon to actually match the road that we wanted to match. Okay, looks good. So next we are going to create a polygon, but it's going to be all in Julia. The objective now is to create a circle around a point. So it's going to be a perimeter around the point. The point we can just reuse the previous one. Just going to use the same one as before on the point 1. Yeah, first we are going to create our structure for Geodesy. So once again, it's different from GMT to Geodesy, both the latitude and the longitude. Okay, it seems okay. Let me run it just check. Okay. So it is imported. Now I'm going to change from latitude and longitude to UTM. Same thing as we did before. TMZ. Okay. And we already have the X and I on UTM for the zone 31. As we have seen before, this is correct. Now I'm going to select the number of sides for our circle, because I'm going to do this manually. I'm not going to use any toolbox for the circle, and I'm going to show you how you can do it as well. Then I'm going to define, based on the number of sides, all the points that I'm going to have on my circle. If I use a low amount of points, then the circle is going to be, well, almost like a triangle, square. It's going to depend on the number of points. But if you use a lot of points, then you are going to approximate very well to a circle. So it's going to be from 0 to 2 pi, my number of sides. 5 actually it's going to be too low for a circle. 50 should be a good enough amount of points for the circle to actually look like one. And then the radius. I'm just going to create something big so you can see how it looks. By the way, it's on meters. Then let's create our circle here. And I'm going already to start creating my polygon. So I'm going to use the point as the basis, plus my radius multiplied by cosine. It's a vector, so we need to use the broadcast function. And this is good enough for the x-axis, and then for the y-axis. It's pretty much the same, but as I want a circle, I'm going to use the sine function. So if one is 0, another one is 1, and if one is 1, then the other one is 0. This is going to allow us to create our circle over here. And then I'm missing something. It's not only the x and y. I also need to define the zone. And if it is north or not. That is not defined. Oh yeah, need to run all of this. Okay, so let's check what's wrong. Oh, it's a point. Okay, perfect. We now got 50 points plus 1. and actually this is expected because I generated an angle from 0 to 2 pi, and the 2 pi is just going to be 0 once again. The function is periodic when we use both the cosine and sine. So the first point is actually going to be the last one. Why did I do like this? 50 plus 1. And it's in order for me to have the same origin point as the last point as well. So we can create our polygon. As I've said before, we need to have both the last point and the first the same in order for us to have a closed polygon and not, for example, a line. Okay, so the circle should be created. I just need to convert from UTM to, once again, latitude and longitude. Well, I don't need to, but just for everything to be on the same, well, to be in line, I guess, I'm just going to put here the transformation as well. But we could reuse the same one here on top, no issues. So it's pretty much going to be the same here. I'm just going to change the variable names. And once again, it's the same thing. I could even copy. It's still a polygon, that's correct. I was using a different name for the variable here. Okay. And then I will just print everything with my function gmt2kml. I'm going to print my variable poly. Once again, it is a polygon, so I need to add f equal to p. Then I need the text. And let's just write to the file and see how it looks. Output KML. Okay. So let me actually run everything. No errors. Great. The output. Oh yeah, of course it's giant. But does it have the size that I wanted? Yeah, it's 40. Okay, perfect. 40 kilometers. Actually, I defined the radius. Was it the radius here as well? Yeah, it's fine. Okay, radius. So yeah, we have just generated the circle. One thing that you guys may be curious was the number of sides. Of course, you can just change the number of sides on your circle, but it's going to be, or it's going to look less like a circle. Of course, also it's going to occupy less space, but like a low poly circle. This is no longer a circle. At least it doesn't look like one. I mean, you could even try to create geometrical shapes. So, for example, if you want a square, then you only need 4 sides. Oh, let's give it a look. There you go. You got your square. Of course, the square still has the same rules as before, with the radius of 40 kilometers. So that was defined on the code. Or a triangle even. Okay, perfect. Now, of course, I'm using Google Earth to display these polygons that I'm drawing, but you don't need to. There is also some functions on the GMT toolbox that allows you to plot. So you can also use plot with the GMT toolbox. Yeah, so for that you can just use coast and select on the European region, and GUI gives you the color of the ground that I'm going to be define as green. But of course, I can change this later. And you don't even need to select the color. If you want to have the same color as the water, you just remove this parameter here. And then plot with exclamation point, because I want to use the same plot as the one used for the coast. My data, actually, no, I call it poly. Poly show true. Okay. Let's give it a look, see how it looks. Okay, perfect. So we got here our Europe map and our triangle, of course. Originally, we want to create a circle. Let me quickly create a circle over here. 50. So just to show you guys, you don't need to have a color on the landmass. You can just remove this. And maybe you actually want to define, well, a color for my polygon. That's a good idea. For example, blue. Okay, let's see how it looks now. So hopefully we are going to have a blue circle. And there he is. Perfect. Okay. And this actually ends our short introduction for geospatial functions on Julia. If you guys want to learn a little bit more of this field, let me know in the comments. We can, for example, create several polygons and create intersections between polygons or unions and then plot everything on a map. Let me know if you guys are interested on this field, and I could even create another tutorial on the same field. Yeah, but for now, this ends our introduction tutorial. Hope you guys have liked it, and I will see you again on the next tutorial.